a no calculator problem. There's a bunch of my work and answers right there. And then if I slide this up, I have some more additional work up here that I wanted to have some neat room for that stuff right there. But when they give us G is the integral of f, right away, I'm going to go G prime, the derivative of the integral is the inside function. So G prime is equal to f. If I take the derivative of each piece there, G double prime is equal to f prime. So that's going to be key. And this is the graph of the f, which is the same thing as the G prime graph right there. All right, so for part A, it says what integrals is the G concave of? So let's talk ourselves into the correct answer right here. Let's do that justification part first, and it'll already be done. We know a graph that G is concave up where the second derivative is positive. The second derivative of G is equivalent to f prime. So if I'm asking where G double prime is positive, that means I'm asking where is f prime positive. Now, since I gave you the graph of f, if I gave us the graph of f prime and said, where is f prime positive? You're looking at where the f prime graph is above the x-axis. But if I give you the graph of f and ask you where is f prime positive, to get from f to f prime, that's a derivative, which is the slope, right? So I want to know where the slopes of this graph is positive, which means where is this graph increasing? So I'm looking, where is this graph going uphill? So I'm going uphill in between the x equals -4 and x equals -2, and also between x equals 2 and x equals 6. And it tells us open intervals, which we always use. And so I got my answer right there. And then I already have my justification there. They want to see that's where the G double prime, which is equivalent to f prime, that's where that's positive, or where the f is increasing right there. So talk yourself into that right answer there. All right, we got plenty of practice kinds like that. All right, part B, I got most of my work right here, but I got a little bit of it up above there just to keep it everything nice and neat. So for part B, they give us P is this function, G of x times f of x, and want us to find the derivative. All right, we're strong with this. We know how to take the derivative. You got to recognize that this is a product, which means to take that derivative, we need to apply our product rule. So we'll go first times the derivative of the second, plus the second times the derivative of the first, and then let's plug in the 3's for all of those items. And now we have to get those items. So that's where the understanding part comes from. The toughest one to get is the first one. G of 3 means we got to take the 3. G of 3 means take the 3 and plug it in for x into your G function. This is our G function right here. So G of 3 is the integral between 0 and 3. That's where I got my work for right here. So I want to integrate this f function. That's the area in between 0 and 3. Now, in between 0 and 3, in between 0 and 1, I have a rectangle here that's 1/2 times base times height. And then in between 1 and 2, I have a triangle above and a triangle below. I guess I didn't really need to do 1/2 base times height minus 1/2 base times height. I should have recognized, hey, I got an equal triangle above and below. So those areas are going to just cancel out like they did right there, because one's above, one's below. So the ones that's below the x-axis, you make that negative. And then what we have here in between 2 and 3, I drew these little lines in here. I have a trapezoid right there. Now, since it's below the x-axis, I have a negative in front of it. And I did the area for a trapezoid. So remember, we add up the bases and divide by 2, times it by the height. So I'll go base 1 plus base 2. So I did 3 plus the 4 divided by 2. So you average out the bases and then times it by the height, which is equivalent to 1. That was the 7/2, but then it was below. So it was a negative 7/2. So that's how I'm coming up with the G of 3. The f prime of 3, this is my f graph. We know the derivative, the f prime means derivative, the derivative means slope. So I want to know what's the slope of this graph at x equals 3. So at x equals 3, it's just a line. So I'm going to go up 1 over 1, up 1 over 1. That slope is equal to 1 right there. So that's how I'm getting the 1. And then f of 3, this is my f graph. If I want f of 3, that just means on my given f graph, when my x is equal to 3, what is our y value right there? So when x equals 3, that y value is a -3. And then the same, that's how I got the -3 there. And then G prime of 3, G prime is equivalent to f. So G prime of 3 is the same thing as f of 3, which is what we just got done talking about right there. That's just that y value right there, which is another -3. So I had -7/2 plus the 9, which is an 18/2. You can add those up, get that 11/2 answer. All right, let's be careful with our notation on letter C. This is a pretty basic L'Hopital's rule problem, but we have to be careful with the notation. You have to make sure you write your limit notation down when you take the derivative of the top and bottom. But first things first, well, I got this limit problem. When I plug in the 2 for the x's, I get 4 minus 4 on the bottom. I get 0 on the bottom. And when I plug in 2 here, G of 2, that g of 2 is like taking the 2 and plugging that in for x. So that's the integral between 0 and 2 of that f function. And that's like kind of what we talked about here. In between 0 and 2, in between 0 and 1, I got that triangle above. And in between 1 and 2, I got that same area triangle below. So that's just going to be 0 because those are just going to cancel each other out there. So I do get 0 on the top, 0 on the bottom. So let's be careful with the notation. Don't put equals 0 over 0 because that's technically not equals. It's in the format. It's in the indeterminate type 0 over 0. So if you want to write 0 over 0 to the side and then just mention, hey, we're going to do L'Hopital's rule here. And then make sure when you put this equals, make sure if you don't have that limit notation there, they're going to be picky about that. All right. Because it's not equal to the derivatives. That's what the limits are equal to each other. That's what the L'Hopital's rule says. So make sure you keep your limit notation in there and simply use your easy L'Hopital's rule. Take the derivative of the top, take the derivative of the bottom. And now I know I'm not going to need to do L'Hopital's rule again because when I plug in 2 to that bottom, you're going to get 2. So automatically, I don't have 0 over 0 or infinity over infinity. But if I plug in 2 to the top, we have to calculate now g prime of 2. So since g prime is equal to f, g prime of 2 is the same thing as f of 2. And I give you the graph of f, or they give us the graph of f. So f of 2 means, hey, on this f graph, when x equals 2, what is that y value? That's why I'm getting that -4 to get that -2 answer right there. So pretty easy L'Hopital's rule problem. I like that problem there. Just be a little bit careful. Make sure you write your limit notation down for that stuff until you plug in and get an answer for it. Then you don't need to keep writing that limit notation. All right. Part D with the theorem problem, it wants us to first find the average rate of change. All right. So remember from your blue packet, your average rate of change is just your slope formula. So I'm going to go g of 2 minus g of -4 over 2 minus -4. So just do your slope formula. G of 2 we said over here was 0. G of -4, I went to the top here. I'm taking -4 and plugging in place for that x. So here's my work for g of -4. So when I'm integrating between 0 and -4, we should have the least the greatest. So I'm going to flip it. And then when you flip it, that changes the sign of the integral. So make sure you stick that negative out there. And then you're going to do the area between -4 and 0. So when I went in between -4 and 0, it wasn't like one trapezoid where I could do one area. So what I did, I drew in this little line segment right here. And I did 1/2 base times height. So 1/2 times 2 times 6. And that was all positive. So it's above the x-axis there. So keep that positive. So there's the area of that triangular piece. And then in between -2 and 0, you have this trapezoid. There's the bottom, here's the top, and then there's the height. So I averaged out the bases. We're going to go 4 plus the 6 divided by 2, and then times it by that height, which is equal to 2. And then so then that negative was just in front of all of that stuff. Everything was above the x-axis, so that was all positive. The 2's canceled out. I had 10 plus 6 to get that 16, carry down that negative. That's why I'm getting this -16 right here. Minus negatives plus a positive there. So you're going to get 16 over 6, which is 8 over 3. You could even have left that at 16 over 6. You would have gotten full credit for that. Remember, if the fractions ever get too large or something, you don't even have to reduce them. You'll get full credit as if you just leave it like that. So that's the first part of that is average rate of change. Just use your slope formula. The second part of that says, does the mean value theorem guarantee a spot where that g prime of c is equal to the average rate of change? So the mean value theorem says this. It says that the derivative is equal to the average rate of change as long as your function is continuous and differentiable. It's got to be continuous and differentiable. Then the mean value theorem is going to guarantee that. So I got down here, yes, the mean value theorem does guarantee since g is continuous and differentiable. So it tells us g is this function here. It says f is a continuous function, all right? But so what we know is g prime is equivalent to f, okay? So when you say g is differentiable, that means the derivative is defined, okay? You have an answer for your derivative. Since g prime is equal to f, this is your f graph. F is defined everywhere. F is defined everywhere. There is a y value for every single x value right there. F is defined everywhere. So if f is defined everywhere, g prime is defined everywhere, which means that g prime is defined, which means g has a derivative, which means g is differentiable, okay? If you're thinking this, some of you might be thinking, well, we got the corner points, we've got the multiple tangent lines. That means f is, you're not even looking at that because let me try to clarify here. If you're looking at this and saying, hey, I got the corner points right there, which means f is not differentiable. That is true, all right? F is not differentiable, which means f prime is undefined someplace. But see, F prime is equivalent to G double prime. I don't care about G double prime at all. I don't care about F prime at all. So while this graph is not differentiable because you got the multiple tangent lines and the corner points, that you're only looking at that as if I'm talking about F prime or G double prime, but I don't care about that at all. For the mean value theorem to guarantee something, the derivative has to exist, all right? And the derivative of G is F, the F exists everywhere. There's a point right there. So like F of -2 is equal to 6, which means G prime of -2 is equal to 6, which means the derivative of that G graph at -2 is equal to 6. So it is differentiable right there. Puppies.